Good morning, everyone. Today I'll be presenting my transferred phenomena assignment. The topic is heat conduction with a viscous heat source. Let's get started. Here's a quick overview of the four problems we'll be covering today. 10.A.3 deals with the viscous heat in cylindrical oil film, especially a curd flow problem where we find the maximum temperature in a lubricating oil. The next problem applies a similar concept, but here the material is different. And the third problem we'll be discussing will be of the counter current double pipe design heat exchanger, and we'll be getting the length of the heat exchanger by LMTD method. The last problem is the most mathematically involved, viscous heating inside a tube carrying laminar flow, where we solve a partial differential equation for the temperature profile. So in this problem we have given that oil acts as a lubricant between concentric cylinders, and the cylindrical rotates at about 7908 rpm. The radius is 5.06 centimeter and the gap is 0.027 centimeter. And both wall temperatures are 155 degree Fahrenheit. So if I'll draw that cylinder, it will be like, here's one cylinder, here's another cylinder. The gap is very small. I am noting that as B, and gap, as I have mentioned, is 0.027 centimeter. The walls are at 155 degree Fahrenheit, both the walls, and in between is there a viscous liquid, and we have to find the maximum oil temperature of that viscous liquid. So we'll be moving ahead with our assumptions. Steady state incompressible Newtonian fluid, narrow gap. So what we mean here is, as the gap is very narrow, we'll be treating this problem as there are two plates and fluid is between those two plates here. Will be, and velocity in theta direction is the velocity in y direction in our assumption, and there is no pressure gradient and pure shear driven force. The important physical idea here is viscous dissipation. The rotating cylinder shears the oil. The mechanical energy does not just disappear, it gets converted into heat right inside the fluid. So even though both oils are same temperature, the oil in the middle gets hotter. This phenomena is characterized by Berkman number. As you can see, the Berkman number is here. Let's move ahead. So now for the solution, we'll follow 4 clean steps. And step number 1, we'll solve the momentum equation for steady co-ed flow. The velocity profile comes out linear. U equals U times Y over B, where U is the wall speed and B is the gap width. Step 2, write the energy equation. In step 2, we have to write the energy equation. Since the conduction must balance viscous dissipation, we get K times double derivative of time with respect to the direction, which is the y direction, plus viscosity into U divided by B whole squared, viscous dissipation. On the step 3, we'll integrate twice with the temperature profile, applying the boundary conditions. The boundary conditions are both wall temperatures we have given, and we'll get a parabolic profile. What I mean by parabolic profile is the profile will be like a parabola in nature. Step 4, the maximum differentiating setting equal to 0 gives the midpoint, y equals b over 2. So just like when we need to find out the maximum of any equation, we differentiate it and we put it to 0. We'll be doing that here only. And the temperature rise of the wall is mu squared over 8k. Plugging in the numbers and angular velocity converts 8 to 8 radians. We have converted the radians here into seconds. The velocity we get is 41.9 meters per second. and by given formula we have found out that the temperature rise was 8.8 degree Celsius, and since we need to find the maximum temperature, that will be the summation of the original temperature, which was 68.3 degrees Celsius or 155 degree Fahrenheit plus 8.8 degrees Celsius. That's for this problem. We'll be moving ahead with the same problem, and here the key concept that we are using the key concept that we are using stays same, that is the quiet flow, and the material only is different. We'll be dealing with a friction bearing temperature rise. All the values are given. The conductivity is 4 into 10 to the power minus 4 calories per second centimeter degree Celsius. Wall temperature are given at 200 degrees Celsius. Speed is 4000 rpm, and geometry is same as of the previous problem, as we have seen. First we have to convert the K, as this is not the standard denotation on step 1. Then we'll be converting the omega from rpm to radians per second, because that's the standard value. Also the u velocity will be converted into meter per second, and by applying the formula, which is change in temperature equals nu into u squared divided by 8k, and doing the calculations, will finally get the temperature difference as 31 degrees Celsius, and the maximum temperature will be summation of 200 plus 31, that will be 231 degrees Celsius. And we'll be moving to our next problem, 9.9. So here in this problem, a countercurrent double pipe heat exchanger hot oil flows through the annular region. If I mark, this is fluid B, here is the fluid A. In the background, part A asks us to write the macroscopic energy balance. We have to do the energy balance of the macroscopic at steady state with the no heat generation. These are our conditions. The heat gained by fluid A equals to heat lost by fluid B. That is the condition. This gives us Q equals m dot times Cp times the temperature change for each stream. Part B asks us to differentially balance over the element dz. We'll be taking a small element of dz here, and we'll be performing the differential balance in the B part. Fluid A is nothing but the mass flow rate of the A into Cp upon the temperature over that dz equals to U into P into temperature of V minus temperature of A. And similarly for fluid E, we can say that. And this gives us the two couple of ordinary differential equations relating the temperature gradient of both fluids to the overall heat transfer coefficient U and the perimeter P. And here we also have to justify why we are using the counter current, because it gives a higher log mean temperature difference, a more uniform driving force along the length, and lets you achieve a closer temperature approach. It's simply more thermally efficient than co-current. That's why we are using the counter current here. And we'll move on with our calculations on the next slide. As we have here, we have the hot oil temperature that's given 130, and the hot out temperature at 80 degrees Celsius, and water temperatures are also given. Water is coming in with 30 degrees Celsius and coming out with 70 degrees Celsius, and heat transfer coefficient is nothing but 1100 watt per meter square per Kelvin. Once we all know the four temperatures, step 2 will be calculate the heat duty Q using the water side. 1 kg per second times the 4180 joules per kilogram Kelvin that you can see that this is nothing but the kilogram per second. 4180 is the joules per kilogram Kelvin, and 40 degree is nothing but the difference in water temperature. This is nothing but difference, and we get, it gives us 1.672 into 10 to the power 5 watts. And we'll next on step 3 we'll do the LMTD calculations, calculate the long mean. We'll be calculating the long mean temperature difference. Delta T is given as 60 degree for hot oil, and delta T is given 50 degree for, it's not for the hot oil, that's the inlet and outlet differences that we are calculating here. And by calculating the LMTD we get 54.9 degree Celsius. And for step 4 we'll find out the required area, that is needed for the heat transfer with the formula A equals to Q over U times delta log mean temperature difference. And by calculating this we found out to be 2.77 meter squared, and as we got the area from that we can get the length by simpling putting in the formula L equals to area upon pi d, as this is the curved surface area of a cylinder, and we found out the length to be 35.3 meters of the exchanger. That will be for the problem 9.9. And we'll be solving problem 11 D.2 here. This is the most mathematically rich problem we have. We have a Newtonian fluid in a laminar flow through a circular tube moving fast enough that the viscous heating is significant. So what is happening is a laminar Newtonian fluid is flowing in a laminar region through a circular tube, and that is moving fast enough so that the heating is significant. The inlet temperatures are uniform, the velocity profile is fully developed, and all the properties are constant. As we can see here, fully developed profile, all properties are constant, viscous heating important at high speed. Velocity, the velocity profile we are getting is nothing but a standard parabolic velocity profile. As you can see, the change in temperature and the relation we have here, and the viscous dissipation term is nu times derivative of velocity with respect to r squared equals to change in pressure squared into r squared divided by 4 into nu times L squared. And substituting into the full energy equation in the cylindrical coordinate gives us the PD involving both R and Z. To solve that, we decompose the temperature as T equals to Tm of Z plus theta of R, where Tm is the bulk mean temperature that rises along the tube, and theta captures the radial variation of the temperature. As you can see that we have decomposed the temperature here in this equation. The boundary conditions that are given are, first of all, the symmetry at target. That's symmetry, that is, this equation is showing the symmetry line at the center. dt by dr equals to 0, and specified wall temperatures are R equals to R is given, and at inlet the temperature is uniform. These are the boundary conditions. So in solving that, we need to follow these 3 points that are given. For a large z, the partial derivative of temperature is that this equation is fully developed. Separate R and we have to separate the R and Z dependence in the equation and solve the ordinary differential equation over theta, and we'll have to integrate that twice. Let's move on. So after doing that, basically separating the differential equations and integrating, we get two constants, C1 here and C2 here, as you can see that. T and Z is nothing but the bulk mean temperature, and it rises along the Z. It rises with Z due to the viscous dissipation. As we can see that this is nothing but a quadratic equation in terms of R, and this contributes as the parabolic contribution. This will have the same shape as the velocity profile, dominant and moderate viscosity, and this is a quadratic correlation we have found out from the coupling between parabolic velocity and radial conduction. That's why we got the quadratic correlations. And at high flow speeds, the viscous dissipation heats the fluid even without wall heating. That you can see that at very high speeds, when the speeds are very high, the friction acts, and due to that, heat is generated in fluid even without there is no heating of the fluid. And regardless of the wall conditions, there will be heating. So we have to move ahead. And after that, so after solving the ordinary differential equation, we have got this final profile. So let's wrap up quickly with the summary of the four results. On the Couette flow, we used the narrow gap Couette flow conditions, in which we assumed that the flow is between two plates and liquid is in between that, and we found out the maximum temperature here. On the second problem, this was a similar problem, but instead we had a low K, and this led to the high temperature difference. The same formula was applied for the friction bearing, gives 231 degrees Celsius. Low thermal conductivity leads to dramatical high temperature. As the conductivity is less, it can't flow. On the third problem, we used the LMTD method, and we found out, using this formula, we found out the area, which was 2.77 initially, and using this area we found out the length of the heat exchanger. And on the last equation, we have to derive the partial derivative. We have to use the PD with the viscous source and quadratic solution to find out the profiles, as we have found out. This was the temperature profile, and this was the bulk temperature. Thank you, everyone.